Good morning to all. Today we are discussing pair production, and remember that we are we have already discussed Compton effect and mm, photoelectric effect in this regard. So let us consider the pair production uh, process. In the pair production, a photon interacts with the nucleus and produces two particles. One is electron and another one is positron. That is, particle and antiparticle pair is produced in the vicinity of a heavy nucleus. And as you can see, we can visualize this process as this one. Gamma photon is going to give you in the final state as E plus and E minus, where E plus is positron and E minus is electron. As you can see, the rest mass energy of electron is 0.511 MeV. So for two particles, one is positron and one is electron, the threshold energy must be 1.022 MeV. That means if we want to observe the phenomena of pair production, we must have 1.022 MeV energy of a photon at least. Now consider the uh, now consider the other aspect also. We can visualize and understand this phenomena using the Feynman diagram also. So let us see the Feynman diagram here. See, there is a photon here which has got the energy, it is equal to E and P momentum, which you can see. And similarly, this photon is interacting with the nucleus that is sitting here, and in this process, first of all, it produces positron, and then this interaction further gives me a virtual electron. This electron is then scattered in this direction, and in the final state we have one is positron, one is electron, and the recoil of the nucleus which was in the vicinity of this whole process. If you see, consider the uh, energy of energy conservation of this whole process, then you know that incoming energy was E and momentum was P, that is E by C of the incoming photon, which is above the threshold energy that is required to produce the pair. Then you have the energy conservation. So H new energy of the incoming photon must be equal to energy of the electron, energy of the positron, and energy of the recoiling nucleus. So E plus E minus plus EA. So that is the conservation of energy, right? Similarly, if you want to consider the momentum conservation, then you know the incoming momentum was the momentum of photon, and photon is a zero mass particle. Therefore, P vector is nothing but h nu upon c in the direction of the incidence, right? So this is the momentum which should be equal to the sum of all the three particles momentum in the final state. Okay, so we can say the momentum of the recoiling nucleus, that is this one, and the momentum of the positron, that is this one, and the momentum of the electron, that is this one, the sum of all the three must be equal to the momentum of the incoming photon, that is equal to P. These two considerations, if well considered and calculated, then we can understand the pair production. Now in the next step, let us see what is the maximum possibility of the momentum of the nucleus. Because it is a three-body process in normal case, then the maximum momentum that it can have is equal to a momentum of the incoming photon. That is, if you see, that is Pa magnitude must be equal to h nu by c, right? So if using this thing, if we estimate approximately what should be the maximum energy of the recoiling nucleus, and remember this nucleus is heavy, so let us say, what is it? It is Pa square upon 2a, where a is the atomic mass. Now if I see this, then the momentum of Pa, that is maximum, is h nu by c. So P square means h nu by c, h nu by c upon 2a, and it will give me h square nu square upon 2a c square, where c is the velocity of light. So the estimate for kinetic energy or recoiling energy of the nucleus is E square upon 2ac square, right? And if we estimate now what is this value, so let us see that Ea of the recoiling nucleus, it should be equal to Pa square upon 2ac square, and now taking incoming photons energy as 1.022 MeV, that is just the sum of electron and positron rest mass, because rest mass of the positron and electron, both of them are equal, and their value is 0.511 MeV, right? So, and taking A equals to nearly heavy nucleus, so 200 atomic mass unit, that is U, 200 U, and now calculating for this is 1.022. So you see that our estimate is 1.022 square, and the unit is MeV square upon C square. Okay, and A is 2 into 200, and you know that 1 U is equal to 940 MeV by C square. So if we calculate it, then we will get roughly 1.022 square upon 400 into 940 MeV, right? And therefore this estimate is nearly 2.78 10 to the power minus 6 MeV, or if you go for the approximation, then it is nearly 3 electron volt. So the recoil energy of the heavy nucleus of almost 200 A is equal to 3 eV. That you see that at the energy scale of MeV, This EV is a very small amount of energy, right? Now let us see what is the order of magnitude of momentum of the recoiling nucleus. Now you know that PA is nothing but 1.022 MeV by C, as you see, and mass is 200 U. So 200 multiplied by 940, this is the mass, that is MeV by C square, and moment velocity, that is V. So we will get it as 1.022 MeV by C, that was the mass, and momentum, and 200 multiplied by 940 MeV by C square, that is the mass of the nucleus, and it gives me V by C. The ratio of recoil velocity of the nucleus divided by C, V by C is 1.022 divided by 200 multiplied by 940, and this estimate is roughly this one, 5.5 10 to the power minus 6. So it is of the order of 5.5 10 to the power minus 6 is this ratio V by C. Now if we want to see that it is, you can understand that the velocity of the recoiling nucleus is almost 1 upon 10 lakh times smaller than velocity of light. So it is basically it is a case of non-relativistic phenomena. If using this again, there are other two actors in this phenomena, and a pair of electron and positron. So let us take the typical value of V by C for them is 0.05 to 0.1 range. So typical value if you take, and then we estimate the energy carried away by the electron and positron, and assuming them to be equal. So the characteristic energy that they take at V by C equals 2.05 is nearly MEC square upon 1 minus V square by C square under the root. Now Me is the characteristic rest mass of the electron and positron. So 0.511 MeV upon 1 minus 0.0025 under the root, and this to 0.511 under the root 1 minus 0.01. So it will vary. If I take the value of V by C between 0.05 and 0.01, then I will get these two values, and therefore you will see that energy carried by electron and positron each is 0.512, or you can say it varies from 0.512 to 0.514. So that is roughly 0.003 MeV larger than the rest energy, right? So now we say that what should be the threshold value of the energy in the pair production. You know, 1.022. 1.022 is the energy in MeV units of the rest mass of the pair. Then 0.006 MeV, that is the energy of the pair due to kinetic energy, and 0.000003 MeV. It is the recoil energy taken or siphoned out by the recoiling nucleus. So the total energy you see is roughly 1.028 MeV, which is roughly 0.006 MeV larger than the rest mass energy of the pair. That simply means 6 kV, of the order of 6 kV more. So that is how we say, but this is possible, as you see, this is possible only when you consider the pair production in the environment where heavy nuclei are present. And heavy nuclei, what I mean by heavy nuclei is the nuclei having A equals to nearly 200 units of atomic mass units. And that's why we say that if we want to observe the pair production will be observed only when the energy is greater than 1.022, or maybe roughly you can say 6 kV more than the rest mass energy of the pair, and a heavy nuclei like lead is present in the vicinity. So in that atmosphere, we will see that a photon interacts with the heavy nuclei atmosphere uh, in the vicinity, and then produces a pair E plus E minus, and energy and momentum, very small amount of energy and momentum is shared by the recoiling nucleus. At the uh, same time, electron and positron also share the energy and momentum. Bulk of the energy is shared by the pair, but the momentum shared by the electron and positron is very less. That what you understand here. And and we see that that's why it is possible if you eliminate um, heavy nuclei in from the atmosphere, then it will be difficult to observe. It will not be possible for the pair production phenomena to occur, because then who will share the momentum? Because pair cannot share the momentum that is carried by the incoming photon E by C. It is very heavy. They cannot, being the small particles, they cannot take that much of momentum. And if they take up that much of momentum, then the energy required is very high. So with the given energy, threshold energy around 1.028 MeV, this will not be possible within this energy range. So giving you the flavor of energy conservation, momentum conservation, and bringing relativistic calculation to indicate that the procedure, if the moment you put heavy nuclei in the vicinity, then this whole process is highly probable, cross section is very high, and energy, momentum, share, and conservations are possible with larger probability, and that is what we understand in the pair production. Thank you.